Hello, so today, continuing on from our derivation of the Dirac equation, which will have been a week ago, we will hopefully be deriving, well, first off the Christoffel symbols and then the geodesic equation. So the geodesic equation is, well, hopefully you know what it is, considering you're clicking on this video. But it's the important equation that governs the movement of objects through curved space-time. And so it requires some background knowledge. I'd say it's useful if you've understood the notation that you would have seen in last week's video, the Einstein's summation notation, where you have those Greek indices, mu, nu, rho, sigma, and lambda, I think, will be the ones that are used in this video. And also four vectors and four vector notation. So that'll be like x to the mu, where mu is those Einstein summation indices. Anyway, I think we'll begin. So the first thing that we need to do is derive the Christoffel symbols. So we'll begin with the condition for metric compatibility. So we have this covariant derivative sub rho. So that's our covariant derivative. And that will be of our metric, the metric tensor field, which is this G sub mu nu. So mu, and my mu's and my nu's are going to have to be very good this video, and I don't know if they are going to be, but how, that's probably a decent one. That looks too much like a little gamma though. That's going to be my nu. And that's equal to 0, and that's the metric compatibility that we need to, allow. And what it does is ensure that lengths and angles defined under this, or defined by this metric tensor field G, remain preserved during parallel transport on a sphere. So the main issue here is, well, working with the geodesic equation is we have these spherical and essentially non-Euclidean geometries which have to be traversed, and this allows essentially it's not so much the principle of least action, but it's similar-ish. It will tell you the path of which a particle would take that would be the equivalent of the shortest path, but of course in some geometry governed by that metric tensor G, metric tensor field. So, well, we can expand this now. So, by the definition of the covariant derivative. So, for example, got it. Over rho of G, mu nu, we'd write, and then this is the notation from last week, and we simply use this to shorten everything. Now we'll introduce the Christoffel symbols, which are these capital gamma. That'll be lambda, G sub lambda, mu minus the second. Actually, it's the same symbol. Yeah, that's all right. Mu, lambda. So I think it should be slightly more clear that these are not this G is not a subscript, but I think it's fairly obvious if you know what's going on. Anyway, well, we know this is 0. This is 0, so we can say that partial sub rho of G sub mu nu is equal to the Christoffel symbol times our metric field tensor over mu nu plus the symbol over so the symbol times G over, sorry, that should be Yeah, this is lambda nu, and this is mu lambda. Yes. G mu lambda. Okay. Lots of subscript, lots of superscripts. Now we have an equation, but unknown. Well, these gammas, we don't know what they are essentially. So what we can do is use cyclical permutations and cycle the indices. And so writing those out in full, this is our, we can call this 1. Then our second permutation would be partial. I think this is a better partial than what I've been doing before, which looks more like a kind of B shape. I think that's better, so I'm going to keep doing that. So that's the partial mu g nu rho is equal to this g lambda mu plus that should be mu new mu new mu g sub rho lambda, and then our third permutation would be partial. That was a pretty one. Partial nu yeah. G sub rho mu is equal to crystal gamma super lambda over mu rho G sub lambda mu plus, is that correct? Lambda, that should be lambda rho. And that should be, I was thinking of the wrong one. Thinking of the wrong one. In my mind. So that should be mu rho, lambda rho. Lambda rho, and this should be nu lambda. Yeah, and then this would be like this, and then G sub rho lambda. Okay, these are our cyclic permutations, and all we've done there is permutated rho. Well, what we can say what we've done there is, if I pop it in a big bracket at the bottom, so we've gone rho mu nu has become mu nu rho has become nu rho mu. And that's what we've permutated between 1, 2, and 3. So that's 1, that's 2, and that's 3. Just to make it ever so clear. Now what I'd like to do is remember which way you do it. I think it's 2 plus 3 minus 1. Well, we're going to try that. We're going to try 2 plus 3 minus 1. Which would be 2 is partial mu g nu rho plus I'm not going to write out the full right hand side, I'll do that separately. Nu g of rho mu plus partial rho g of mu nu. Yeah, we can say that's equal to, oh sorry, it should be minus. That's the whole point of doing this. We add and subtract and things cancel, which is really useful. Minus equals to something, and in fact I can write, we can call that right hand side, and what is on the right hand side is gamma. I hope these gammas are okay. I think some people do it like that, but I'm just going to do that, and I think it's quite clear what that is. Mu nu g lambda rho plus gamma mu rho super lambda g nu lambda. Okay, that should be from 1. Just double checking I've remembered that. I do have notes. I did not write this all out in my notes, which is unhelpful, and I should remember to do that in future. If I make a mistake, it'll be very clear, and I'll probably have edited it out, so a very small amount of editing does go into these. Oh, I need to put it in brackets. Nu mu lambda g of rho lambda. That's not a lambda. That's a lambda. There we go. Minus the rho mu lambda. It's not a very good lambda. Lambda g sub lambda nu plus lambda rho nu g sub mu lambda. Right. I promise the hard part goes away once this has been derived, because then it becomes reparameterization of the principle of least action, which is doable. I know it's doable, and there'll be a lot less tedious stuff, because it'll become very clear how this Christoffel symbol gets derived. Anyway, I'm hesitant to write this all out because we have a symmetry for the metric, in the sense that g of g sub a b is equal to g sub b a, and we also have, as long as the indices of the Christoffel symbols are the same, or rather the upper indices are the same, we have symmetry between the lower ones. So that sub AB would be equal to sub BA. So those are our two symmetries. And so terms cancel, and the terms that cancel are mu. So that cancels with that. Yeah, good. And I'll do it in a different color pen because I might make it slightly clearer. That cancels with that, and the other one is nu rho lambda mu cancels with the other negative term, I think. Mu lambda, yeah. Okay, so that's what cancel. And then we're left with these last two terms, which should be identical, and those two are identical. So we can say that the right hand side is equal to 2 times the Christoffel symbol sub mu nu super lambda times g lambda rho. Okay, so now with some manipulation we take things to the other sides, and yeah, so what I'll say here is that the inverse of that the inverse metric of that, or rather of 2, I can write it here, 2g lambda rho, and we can say that they if you multiplied one to the other, they would equal to 1. So the inverse would be half g super sigma rho is equal to 1. So therefore Christoffel symbol, the one that we require here, which I believe is of the second kind, but this is the one that I've derived to be helpful, is equal to half g to the sigma, that's a really bad sigma, sigma rho. I need to get better at drawing these. Sigma rho times all of those partials. Partial mu g nu. That's not a nu. Nu rho plus partial. Goodness me, they're horrible. Nu g rho mu. Oh, minus. Don't forget, it's a minus there. Minus partial. I did write this down, so I'm gonna check now that this adds up. Or rather, I know it adds up because this is what I wrote out here. Okay, I didn't make any mistakes because those actually do cancel out, and those actually are the same thing. Wow, that's lucky. I'm not sure how Herr Einstein did this. Did Einstein even derive this equation? I ought to provide context on that. Oh, it says they're named for Elwin Bruno Christoffel, who died in 1900. Because he developed tensor calculus. No, they were him. In his 1869 paper Über die Transformation der homogenen Differentialausdrücke zweiten Grades, on the transformation of homogeneous differential expressions of the second degree. Excuse my accent, it was terrible. 5 years of GCSE German taught me nothing, obviously. And regardless. Anyway, we've shown the metric. In fact, the better way of defining the inverse metric, I should probably write it out a bit better than that. There's not a very robust definition. What do you mean 1? Delta sub lambda super sigma sub mu nu lambda is equal to, yeah, that's the more, it has come to my memory that that's a slightly better way of writing it. So that's our inverse, and that should be down there, which is what I've got wrong. That's sigma and that's mu nu. Okay, anyway, we have the definition of the Christoffel symbol of the second kind. And now we can continue, and this will come back later to be very cool. Anyway, now I'll draw a line just to show that we're moving on. The principle of least action. Well, delta S, that was the Wadsworth delta. Delta S equals 0. What is S? S is the integral of the Lagrangian. That's a slightly better Lagrangian. In this case, d lambda. And lambda is, I wrote it down, and it's, oh yeah, it's the metric, or like the distance metric, for what you, or it's like time, but not really, because this might not be applicable for time. So it's some metric against which everything is taking place, I guess. Maybe not the most robust definition. That's a horrible integral, so I'm going to rewrite that. L d lambda. And now we can write this, the Lagrangian here being this integral of g sub mu nu x dots to the mu x dots to the nu, where x dots would be our full velocity, and x is our full position. D lambda looks like a partial. It's a better partial than most of my supposed to be partials. Anyway, now to find the stationary path, we have to solve the Euler-Lagrange equation with some specific coordinate x rho. As a reminder, the Euler-Lagrange equation for this, why do all my d's look really good now? d lambda partial L partial x dot rho minus partial L partial, ooh, that's really bad, x to the rho equals 0. And so Euler-Lagrange equation. And the first step is to find the, so as per usual, I'll find these separately. So I'll do the position derivative and then the velocity derivative. So our position derivative in terms of x rho is just, well, our derivative of the Lagrangian, which is partial x rho of g mu nu x dot mu x dot nu, which is, we can just leave as the partial over rho of g mu nu x dot mu x dot nu, because those aren't in terms of xp. XP? X rho, goodness. Anyway, the next step, we can actually pop that in a bracket, which might be helpful. The next step is the velocity derivative, which is partial of the Lagrangian partial x dot rho, so the velocity at specific x rho. Now we have to use product rule because there's two x dots here. So this is because no longer in terms of our metric tensor, or rather we can treat that as a constant here. Partial x dot rho of x dot mu x dot nu, and so product rule, if you remember that, is partial x dot mu over, no, these are really bad, my partials are returning to garbage. X dot mu over partial x dot rho times x dot nu plus partial, I'll leave them in this order actually, x dot mu partial x dot nu over partial, so the partial derivative of x dot nu. Now we know the Kronecker delta, or rather we can just say the identity here, that this, or I think I'll write it out and it'll become more apparent. This is simply the Kronecker delta sub rho super mu, and that's just a shorthand form of writing that. Essentially, we're not really computing any of these derivatives, because why would you? They are ultra specific, maybe not, but they are case specific at least. And then we could distribute the metric, but I can't be bothered. No, actually I can be bothered, because then the delta becomes important. So this delta forces mu into rho, and this delta forces nu into rho, which simplifies things, because then we get that it's equal to g sub rho nu x dots nu plus g sub mu rho x dot mu. Yeah. Okay, that's useful. And we have symmetry here. And because this is just a dummy index, because that's rho nu to the nu, and that's rho mu to the mu. Sorry, x dot to the nu plus g sub mu rho mu x dot to the mu. Now that's useful because we can just changing mu to nu because it's just a dummy. It doesn't matter. It's 2g sub rho nu x dot to the nu. Okay, and I understand that that could be mu as well, but it's more useful. Anyway, now we just compute the final derivative, which is that with respect to lambda, which is just so d lambda of that partial derivative is just the derivative of this, 2g and x dot, yeah, this is why it's helpful, of that, which is, again, product rule, 2 times the derivative with respect to lambda of g sub rho nu, it should all be in terms of rho nu, times x hat nu plus g sub rho nu times the derivative with respect to lambda of x dot to the mu, pop it in a big bracket. This would be the acceleration rather than velocity. And for this we use the chain rule. So d g d lambda, I should just say that that's dg sub rho nu d lambda is partial g rho nu partial x to the sigma times dx to the sigma over d lambda, which is just oh, that was a 2, partial sigma g rho nu times x dots to the sigma, because we know what that is, and yeah, that's just shorthand notation. So that's just a useful expansion. So then we can say that this continues to be 2 times that, essentially. 2 partial sub sigma g rho nu x dot sigma x dot nu plus 2g rho nu x double dot to the nu. Okay, right, so we've worked out what everything is. And we can equate the position and time derivative terms now. And we can definitely do some cleaning up of things, such as dividing it. Let's write the whole thing out, shall we? So we have that 2g sub rho nu x double dots to the nu plus 2 sigma g rho mu x hat nu minus partial rho g mu nu x dot mu x dot nu, don't need to put that in a bracket even, is equal to 0. We can divide everything by 2, pop a half in there, and now the most useful thing is relabeling indices. So mu becomes sigma, and these sigmas are getting worse and worse. What's the best way to draw it? Like that, I think. Okay, mu becomes sigma, and nu stays nu. So then this becomes G. There's just a lot going on, so bear with. Plus partial sub sigma G rho nu x dot sigma x dot nu minus half partial sub rho G sub sigma nu x dot sigma x dot nu equals 0. Oh, and now we can factorize out. Yeah, we can factorize stuff out. Yeah, because we have that in both of them. So I'll pop that in brackets just to make it very clear. And so G rho nu x double dot to the nu. This may turn out to be quite a long video, unfortunately. But it's okay. I'm sure it'll be enjoyable. It's quite a mammoth task. Sigma G rho nu minus a half. This is just factoring out what we have left over. That should be sub rho G mu nu times x dot sigma x dot nu is equal to 0. Right, so this is getting useful because now we have a solved, or not solved, but we have an Euler-Lagrange equation. And the last thing we can do, or rather the next thing we can do, I don't think it's the last, is symmetrization. Symmetrization. Sorry, symmetrization. So what we can say is x dot sigma x dot nu is equal to x dot nu x dot sigma. So it's not position dependent, which is useful. The only symmetric part of the coefficient, which is this essentially, contributes to the sum. And what we want to do here is force symmetry, and how we do that is split the term into two identical halves and then swapping dummy indices in the second half. So if we now take this rho nu x dot sigma x dot nu, that's equal to half, because we know that this is symmetrical, or rather we can force symmetry, plus another half sigma, partial sub sigma. And remember, this is just our shorthand notation for the derivative with respect to the subscripted variable. Rho nu x dot sigma x dot nu. Okay, and now we just relabel our secondary terms. Sorry, relabel our sigma as nu in the second term. Note that sigma and nu are interchangeable. And we need to change which one? This one needs to become a sigma. Yeah, and then which should be equal to, and then we can factor half times partial sub sigma G rho nu plus partial nu G rho sigma x dot sigma x dot nu. And we can substitute things back into our main equation now. And say that G rho nu x double dot nu plus that whole thing, not that whole thing, plus that part, half bracket I'm going to copy it because I'm getting tired of rewriting it every time. Oh look, perfect. Minus half. If you don't like writing things again and again and again, don't do physics. Rho G sigma. That's a joke. Always do physics. Physics is the best. X dot sigma x dot nu equals 0. Controversial take, but physics is way better than maths. Anyway. I mean, you can kind of just get rid of those square brackets. But the really important thing here is that this factorizes to become half sigma that G blah, 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 blah. It's what physics just driven me to. I don't have the brain power to speak all of this as I'm writing it. But if we well, actually we can kind of just leave it like that, but there's one more step that we need to do before we end up doing this. We need to isolate the acceleration first. Anyway, you can put that in a bracket or something. That would be x dot sigma x dot nu equals 0, and obviously plus our g rho nu x double dot nu. Very cool. We're nearing the end. We're nearing the end. Might finish in 45 minutes. We want the acceleration on its own. The coefficient is that, and so now we just, well, using the identity matrix, we know that's g lambda rho, g rho nu is equal to that delta nu lambda, which is just our identity matrix in this case. So g lambda rho, g rho nu x double dot mu plus g lambda rho times, half dot 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 equals 0. It doesn't matter too much for this. And so if we then factor that out instead, because it's all a product, that's just our thingy. What's it called? Kronecker delta. I think, yeah, Kronecker delta. Or it's just our identity matrix. Super lambda x double dot nu plus a half g lambda rho times that whole sequence from above, dot dot dot, x dot sigma v dot nu is equal to 0, and that's just the identity matrix, so that can be scrubbed out, or rather you can, it's just going to be the same thing for our 4 acceleration. Anyway, that pretty much brings us to the end, because we know that that middle term is precisely our definition of the Christoffel symbol from above, so I guess the desired shorthand notation here for the geodesic equation is x double dot nu plus, that should be sigma nu to the power of lambda x dot sigma x dot mu equals to 0. And that is our completed geodesic equation. Derived from the principle of least action, which is essentially reparameterization of. But yeah, I don't know why I do this. Every time when I go to take a thumbnail screenshot, I'm like, why do I go up to the top every time? But I think it's kind of cool to reflect back on everything that's gone into this. But yeah, I hope that was somewhat enjoyable, if not quite long and ever so slightly painful. But it was done, and now I won't have to do it again because I've written it down. And I hope that makes sense. Anyway, yeah, I'll see you next week for another video. Bye bye.